Thank you, David. Questions? Lev?
Yes, I think I mentioned to you in the coffee break before. It cannot be a proof that the quantum system is not described by quantum wave, because your tomography is made on pre- and post-selected ensemble. So your quantum system is going to be described by two quantum waves, one going forward and one going backward. There is no any contradiction with stating that if you don't make post-selection, the system is described by one system described by a quantum state.
But the post-selected sub-ensemble, first of all, let me say that if we look at this in terms of the two-vector formalism, because we're starting off with a maximally mixed state, we're getting no information coming from the past. So that's why the vector coming from the future dominates. The only information is coming from the future. Therefore, it forces the ensemble to be in four sub-ensembles which reflect that future measurement. So the two-vector, I would say the two-vector formalism, I agree with you start off with that, but it collapses into a one-vector formalism because the forward-going state is maximally mixed. And the reason why you can't give the state to the quantum system is because you can pick out this sub-ensemble which is entangled.
This last statement I don't understand. Your system is described completely by a density matrix, completely unknown state from the past, and your phi state which you measured in the future. So, and this is what you find in your tomography. I see no contradiction whatsoever with wave function description, but your main point that you say that quantum system without post-selection, this is how it sounds, that your conclusion are really that the system need to be described by ensemble. And usually in standard quantum mechanics, people don't talk about pre- and post-selected system. They talk about pre-selected system. If it's not so, to show that this is wrong, you have to show experiment in which pre-selected only system will not some wrong tomography. And your tomography was made on pre- and post-selected ensemble, which is correctly described by two-state vector, in which here the forward one really didn't get information, as you say. But the backward was exactly the phi plus, and this is what you found. No contradiction with description of a quantum system with a wave function.
What about this equation as a state of a sub-ensemble?
This is a pre- and post-selected system.
No.
Your system is described by two of them.
This is normal quantum mechanics. Normal quantum mechanics applied, given, if you assume that the individual quantum systems have states, then you say that the state of the sub-ensemble is this. Now, the fact is, the only fact that we need about this is that it's separable. By definition, a separable sub-ensemble is not entangled.
The meaning of quantum system, you can use this only for future measurements without post-selection. Of course, if you make post-selection, you get all kinds of strange phenomena. The concept for using the wave function is recipe for making experiment in the future without post-selection. So this might have a meaning only in experiment where post-selection is not present. You add post-selection, you have to add the second one, and then the tomography will be different.
But quantum mechanics doesn't tell me that. I showed you the quantum mechanical calculation, which just relies on Bayes' theorem and normal quantum mechanics. And normal quantum mechanics tells me that I've got an entangled sub-ensemble. So, I mean, I think what you are saying is that the two-vector formalism dominates. If you've got a choice between the two-vector formalism and normal quantum mechanics, you choose the two-vector formalism approach. Because
both are correct, but if you have a system which is pre-selected and post-selected, you can calculate both ways. Anyway, given that pre-selection and post-selection, of course, no one will take into account only the pre-selection information. You have to take into account also the post-selection. You can use the the usual formalism too, and there is then nothing contradicting that. Because standard, you are not supposed, when you make quantum measurement, you say that this room is described by a wave function. You cannot also use only the cases where this we go to lunch 1 hour later. you have to decide at which moment you should take this into account to make prediction when go to lab. But I should stop.
Well, given that you've mentioned lunch lab, yes, we do have that constraint, but we do have time for a quick question in Ken.
So a lot of the analysis, which I quite enjoyed, relied on this idea that, okay, now we know that the past states are entangled. We kept referring to the fact that they're entangled as some objective feature reference, and then got into this weird contradiction. What if my response to the contradiction was to say, well, that just tells me that entanglement is not a state of reality, but rather a state of knowledge. It's not a fact of the matter whether two things are entangled or not.
Well, you know, like you do the quantum mechanical calculation, you get your computer to analyse the quantum tomography data, it hits you with a state for the sub-ensemble, your algebra hits you with a state for the sub-ensemble. Why shouldn't I just treat that as a normal case and accept it? And also, whatever objection you make here to this result, you're going to be able, I think, to make the same objection to delayed choice entanglements problem.
Which I also think is a state of knowledge.
Well, then if you say that, you're in conflict with a significant literature.
Yeah, I think it's characteristic of this field that significant literatures can sometimes turn out to be wrong. Any more questions? Matt?
So quick about what you said about preparation independency in PDR. So of course, if I take the standard PDR assumptions, but then condition the probability distributions on the outcome of the future experiment, then I will get probability distributions that are correlated between the two systems. So that assumption won't hold there. So I don't see how you can make an objection. I'll end up with a probability distribution over the variables for two systems that's correlated. So it doesn't satisfy that corporation, even though I started with that, just by conditioning on the
So this may be the error that we're making. So let me put it this way, so that I'll appreciate it. If I have independent preparations, so that I have a separable ensemble, and they're prepared, I know how they're prepared, so that it's a proper separable ensemble, because I can pluck out of it at any time, a set of 1-1s or a set of 0-0s. So it's a properly separable ensemble. Are you saying that can have entangled sub-ensembles?
And I'm saying if you make the PDR assumption that you have two independent probability distributions representing that, then you have a response function representing your entangled measurement, and then if you condition those probabilities on getting an outcome of that measurement, using Bayes' rule and compute what the probabilities that that phonetic model predicts, it will be correlated if you made a joint measurement.
So what you're saying then is that if you pick out that set of runs, 2, 7, 19, 29, blah, blah, out of your properly separable ensemble, if you pick out a particular sub-ensemble of numbered runs, it can be entangled.
Well, no, I'm talking about what happens at the ontological model level. So
just at the ontological
I
level.
agree at the quantum level you have this great entanglement, but the analog of that is to condition the classical probabilities on the outcomes, in which case you get a correlated distribution. So I just don't see how there's an objection against preparation independence from that.
At the ontic level?
Yeah.
Oh, I see. Right. Okay, but you think it's okay, the argument's okay at the quantum level? I mean, that would reassure us greatly if...
I mean, in the sense that there is a backwards state which you can use for computing the outcomes of things. I don't see that there's a problem with that. But I don't see how the existence of that is an objection to the PBR assumption. That's all.
Okay, at the ontic level.
Good. We're out of time, so please join me in thanking you.